Lecture 27, Descriptive Main Group Chemistry, Groups 6, 7, and 8A. In the previous lecture, we began to talk about some of the chemistry of the main group nonmetals, which are dictated mostly by periodic properties such as electronegativity and atomic radius. We took a look at groups 4A and 5A, the carbon and nitrogen groups. Now we're ready to take a look at the rest of the periodic table, groups 6A through 8A. Group 6A is known as the chalogens. This is the oxygen group. In this lecture, we're going to focus mainly on oxygen and sulfur. Again, comparing a second row element to a third row element to compare and contrast reactivity and properties. Let's first take a look at oxygen. Oxygen exists in nature mainly as dioxygen molecules. In an oxygen molecule, there's a double bond between the two oxygen atoms. Again, this is due to the small atomic radius of oxygen, which allows the atoms to get close enough together to form the pi bonds that are needed to form a double bond. Another interesting note about oxygen is that it's a paramagnetic molecule. This means that oxygen is weakly attracted to a magnetic field. This attraction is due to the presence of unpaired electrons in oxygen. Oxygen is a diradical, meaning that there's two unpaired electrons. Typically, when there are unpaired electrons in the structure of an atom or molecule, this makes the atoms or molecules more reactive. We can compare this to nitrogen, where all electrons are paired up. Nitrogen is typically chemically inert in terms of reactivity, where oxygen is a much more reactive molecule, again due to the presence of those unpaired electrons. Another allotrope observed of oxygen is ozone, which is an O3 molecule. Ozone forms through reactions in the upper atmosphere, and a layer of ozone protects the planet from harmful ultraviolet radiation from the sun. Another important thing to observe about oxygen is that it's the second most electronegative element in the periodic table. This affects its reactivity. Most of the time, oxygen reacts with other elements to form oxides, and in those oxides, oxygen has a negative oxidation state exclusively. The only time oxygen reacts with an element to form a positive oxidation state is when it reacts with fluorine, which is more electronegative than it. Oxygen mainly exists in a -2 oxidation state. However, it does have other oxidation states which are also negative. The type of oxide that forms ultimately depends on the size of the other element. If the other element has a small atomic radius, it'll tend to form a regular oxide, where oxygen has a -2 oxidation state. Elements towards the top of the periodic table will tend to form regular oxides. The examples here that we give are nitrogen or nitric oxide, NO, carbon dioxide, CO2, and iron 3 oxide, which is Fe2O3, or the main component of rust. Again, all these elements are towards the top 3 rows of the periodic table and have a small atomic radii, which will be closer in size to the oxide ion. Mid-size atoms tend to form peroxides with oxygen. The peroxide ion is a diatomic ion, O2, with a 2- charge. This gives each oxygen atom a -1 oxidation state. Elements towards the middle of the periodic table tend to form peroxides with oxygen. Some examples are sodium peroxide and hydrogen peroxide. Finally, larger atoms tend to form superoxides with oxygen. The superoxide ion is O2-. This means that each oxygen atom has a -1/2 oxidation state, which may seem very weird. However, you need to recognize that oxidation states are merely bookkeeping devices that we use to track redox chemistry. It doesn't necessarily represent the real charges on atoms, unless those atoms are ions. Superoxides form between oxygen and larger atoms. As an example, we use cesium and potassium. Both are towards the bottom of the periodic table in relatively larger atoms. Another property of the oxides is that they have acid-base nature. How they'll react to form in acidic or basic environments depends on the electronegativity of the other element. If the electronegativity is much different than the other element is much different than the electronegativity of oxygen, then those oxides tend to make a solution basic. This is because any bonding between that element and oxygen will be relatively weak compared to the bond between oxygen and hydrogen. This facilitates the formation of hydroxide ions. Basic oxides include group 1A and 2A oxides. Group 1A being the alkali metals, and group 2A being the alkaline earth metals. When group 1A and 2A oxides react with water, they form basic solutions. An example is the reaction between calcium oxide and water, which forms calcium hydroxide, which is moderately soluble in water. The other extreme is when the electronegativity of the other element is similar to oxygen. This means a stronger bond is formed between the oxygen atom and the other atom versus oxygen and hydrogen. These types of oxides tend to form acidic solutions when reacting with water. A good example is nonmetal oxides. Many nonmetals have more similar electronegativities with oxygen itself. Therefore, nonmetal oxides tend to react with water to form acidic solutions. An example of an acidic oxide is tetraphosphorus digoxide, which reacts with water to form phosphoric acid. There's also an in-between nature, where the oxides tend to be able to react as acids or bases, depending on the situation. This tends to happen with transition metal oxides or oxides from group 3A and 4A metals. We call these oxides amphoteric, which is a general term that means those oxides can behave as acids or bases, depending on the situation. You might remember we talked about another term that meant a very similar thing, amphiprotic. But those types of reactions tend to be more exclusive towards proton transfer reactions, or Bronsted-Lowry acid-base reactions, where amphoteric reactions can also include Lewis acid-base reactions, where electron pairs are either donated or accepted. Here's some reactions between zinc oxide, which is considered to be amphoteric, and different species that illustrate the reactions as acids and bases. When zinc oxide reacts with sulfuric acid, a double displacement reaction occurs where the zinc ion combines with sulfate to form zinc sulfate. The other product there is water. We can see that this reaction more as a proton transfer reaction. The protons from sulfuric acid are transferred to the oxygen atom in zinc oxide. Therefore, zinc oxide is acting as a Bronsted-Lowry base, and sulfuric acid is reacting as a Bronsted-Lowry acid. When zinc oxide reacts with sodium hydroxide plus a water molecule, you form sodium zinc hydroxide. The zinc ZnOH4 that's in brackets is a complex ion. The formation of complex ions involves Lewis acid-base chemistry, where zinc behaves as the Lewis acid, accepting an electron pair from hydroxide. Therefore, zinc oxide is acting as a Lewis acid, and sodium hydroxide acts as a Lewis base. Now let's take a look at sulfur, which is the element in the third row. There are many allotropic forms of sulfur, mainly consisting of rings of sulfur atoms. The most common allotrope of sulfur is the S8 molecule, cyclyl octasulfur. This 8-membered ring has all single bonds between the sulfur. This is another contrast between sulfur and oxygen. Remember that the allotropes of sulfur, ozone, and dioxygen have at least one double bond between the oxygen atoms, because oxygen is a smaller atom and can get close enough to the other atom to form a double bond. Sulfur, as a bigger atom, cannot facilitate the double or triple bonds, because the atom is so large. Therefore, only single bonds form between the sulfur atoms and the allotropes of sulfur. Naturally occurring S8 has a rhombic crystalline structure, as shown in the picture on the right. However, if you heat rhombic sulfur to about 96 degrees centigrade, you get another crystalline form called monoclinic. You can see that the major difference between monoclinic and rhombic sulfur is that monoclinic sulfur has more needle-like crystalline structure. Another allotrope of sulfur is a polymeric form known as amorphous sulfur. Amorphous sulfur is formed from melting sulfur and then quickly cooling it down, which facilitates the linking of chains of sulfur atoms. This is shown in the picture on the right, where molten sulfur is poured into a beaker of cold water, which rapidly cools the sulfur, allowing for the chains to link up, forming the more plastic amorphous sulfur. Now let's take a look at the compounds formed between oxygen and sulfur and make some comparisons and some contrasts. First of all, let's look at the presence of oxides and sulfides in nature. Many elements combine with oxygen and sulfur to form compounds that exist as minerals. However, whether or not the element forms an oxide or sulfide depends on the size. Remember that ions, or atoms, that have similar sizes tend to form more stable, naturally occurring compounds with one another. Therefore, smaller atoms, or ions, tend to form oxides. Here's some examples of some naturally occurring oxide compounds that can be found in the Earth's crust. Hematite is the oxide of iron, and rutile is the oxide of titanium. Both titanium and iron are in the first row of the transition metals, meaning that those ions are relatively small. Also, iron and titanium in these oxides tend to have a very high charge, +3 for iron and +4 for titanium. This means that these ions are even smaller than the atoms that they come in their parent atoms. Again, smaller atoms tend to form oxides that exist naturally in the Earth's crust. By contrast, sulfur tends to combine with larger elements, which have similar ionic radii. Some examples of larger atoms are the transition metals in late main group metals, such as mercury and lead respectively. Mercury combines with sulfur to form the mineral cinnabar, while lead combines with sulfur to form the mineral galena. Another type of compound that we can compare are the hydrides of oxygen and sulfur. We did a similar comparison with the hydrides of phosphorus and nitrogen. Here are the Lewis structures and ball stick structures for water and hydrogen sulfide, H2O and H2S. Also shown are electrostatic potential maps for both molecules. You might remember that electrostatic potential map shows the relative electron density around each atom in the molecule. The more red colors indicate that there's more electronegativity around that part of the molecule, while the blue colors tend to mean that there's less electron density. The greens and yellows indicate electron density between those two extremes. There are two things that you can notice about these pictures. First of all, the size difference between oxygen and sulfur again indicate the incentive for hybridization. Small atoms, as you might remember, tend to hybridize their orbitals to give the electron groups more room. This minimizes electronic repulsion and lowers the energy of the molecule. You can see that the bond angle for water is larger than the bond angle for hydrogen sulfide. The bond angle for hydrogen sulfide is closer to 90 degrees, which is the natural angle between p orbitals in an atom. This means that for sulfur, the sulfur atom is not hybridizing, where in water, where the bond angle is larger, is hybridizing. This is because sulfur as a larger atom does not need to hybridize to give more room to the electron pairs. Those electron groups do have more room because of the larger atom. Also, if you look at the electrostatic potential map, you'll see that water is a lot more polar than hydrogen sulfide. This is because there's a greater electronegativity difference between the oxygen and hydrogens than in the sulfur and hydrogens. This is mainly seen because there's more red near the oxygen than there is near the sulfur. The difference in size and the difference in polarity have two consequences in the reactivity of water and hydrogen sulfide. First of all, hydrogen sulfide is a much stronger acid than water. This is due to the difference in atomic size. Since oxygen is a smaller atom than sulfur, the oxygen-hydrogen bond energy is a lot greater than the bond energy for a sulfur-hydrogen bond, meaning that it's easier to break an SH bond than to break an OH bond, which results in H2S being a stronger acid than water. Another difference is, since the bonds are stronger in water H2S than in H2S, water tends to be relatively inert towards oxidation. This also has to do with the high electronegativity of oxygen. Unless you react it with fluorine, you're very unlikely to cause the oxidation of oxygen in water. However, in H2S, since sulfur is less electronegative, sulfur tends to be H2S tends to be more reactive towards oxidation. The formation of H2S, that therefore is pretty dangerous due to this higher reactivity. Now that we've discussed oxygen and sulfur, let's take a look at perhaps the most interesting group in the periodic table, the halogens, which is group 7A. The halogens are pretty interesting for one reason, for this main reason. All halogens are one electron away from having a complete octet. Therefore, they react relatively spectacularly to get that extra electron. There are a couple of consequences of this. The halogens tend to be the more reactive element within the same row. However, if you look at the halogens as a group, reactivity tends to decrease from top to bottom. This is due to the decrease in electronegativity. The reactivity of the halogens also means that you cannot find halogens as free elements in nature. Halogens were not discovered until the 1800s or late 1700s due to the invention of the electrochemical cell, or mainly in the form of the voltaic pile, which allowed for the formation of these elements electrochemically. Therefore, most halogens are found forming compounds, typically with the alkali or alkaline earth metals, which are the very reactive counterpart in the metal groups. Another consequence of the halogens only needing one valence electron to form an octet is that they tend to form singly bonded diatomic molecules with themselves. Therefore, elemental forms of the halogens exist as F2, Cl2, Br2, and I2. Another cool thing about the halogens that you might have noted from the pictures on the previous slide is the phase behavior of the halogens. Halogens have the most diverse phase behavior in the periodic table in terms of elements within the same group. This has mainly to do with the size of the molecules, which is dictated by the atomic radius. Remember that atomic radius increases as you go from top to bottom down a group. Therefore, a fluorine molecule is the smallest molecule in the group, where iodine is the biggest molecule. Note that we're leaving out acetylene and tennessine since they are generally radioactive and don't get a chance to participate in the same chemistry. This affects what we call the polarizability of these molecules. Larger molecules have larger electron clouds, and the larger electron clouds are easier to distort in many different ways. The distortions in an electron cloud of a molecule is what causes London dispersion forces, which you might remember are the intermolecular forces that all atoms and molecules possess due to instantaneous and induced charges formed within the electron cloud. Since smaller molecules are less polarizable, the tendency is that fluorine has weaker London forces than iodine does. Here's a pictorial representation of those molecules. You can see the size comparison between fluorine and iodine. This affects the phase behavior of the molecules. If you look at the table on the right, you see that fluorine has a lower melting and boiling point than iodine does. You can also see that the melting point increases as you go from fluorine to iodine. The same happens with the boiling points. This is due to an increase in the strength of the intermolecular forces as the molecules get bigger. Vapor pressure, on the other hand, would decrease as you go from fluorine to iodine, meaning that fluorine would have the highest vapor pressure while iodine would have the lowest vapor pressure. This means this has a direct consequence of the phases that these molecules naturally exist as. Fluorine and chlorine exist mainly as gases, while bromine is a liquid and iodine is a solid. Another thing to note is that while there's differences in the strength of London forces are the only intermolecular forces these molecules have. And London forces are generally much weaker than other intermolecular forces like dipole-dipole interactions, the interactions between polar molecules, and hydrogen bonding. This means that all halogens have some sort of vapor pressure at room temperature. For example, of course, fluorine and chlorine exist as gases. Bromine exists as a liquid, but if you look at a sample of bromine, you can definitely see that some of the bromine molecules have enough energy to escape the surface of the liquid to form a gas. For iodine, you can observe the vapor pressure of iodine by taking iodine crystals and putting them in a beaker and covering them with a watch glass. You'll notice as time passes that some of the iodine molecules do make it into the vapor phase, as you'll observe a purple haze over the iodine crystals. Another interesting thing about halogens is their reactivity. Being the more electronegative elements in the periodic table, the reactivity of the halogens usually is redox reactivity. One thing to note is because electronegativity decreases as you move from top to bottom down the group, this affects the ability for those halogens to function as oxidizing agents, or as reagents that can be reduced in order to oxidize another element. We can look at this by looking at standard reduction potentials, which we studied a bit in our electrochemistry unit. If you compare the reduction of fluorine gas versus iodine gas, you see that the reduction potential steadily decreases as you move from fluorine to iodine. This means that fluorine is more apt to being reduced than iodine is. That's right. This means that fluorine is a much stronger oxidizing agent than iodine is. There are some single displacement reactions where we can look at this property and look at a general rule that higher halogens will oxidize lower halides in aqueous solution. Let's look at two reactions to study this effect. If you bubble chlorine gas through a solution of sodium bromide, you get a single displacement reaction where chlorine combines with sodium to form sodium chloride, and bromine liquid is displaced from the solution. In this reaction, chlorine gas is being reduced and bromine is being oxidized. If you calculate a standard cell potential for this reaction, you find that it's positive, indicating that this is a spontaneous reaction. Therefore, chlorine can oxidize bromine in a single displacement reaction. But if we try things the other way around and try to get bromine to oxidize chlorine in solution, we find that the reaction does not occur. Calculating a standard cell potential, we find that it's a negative 0.27 volts, meaning that this reaction is non-spontaneous. If we look at the other elements in the other halogens, we note that fluorine, being extremely reactive, is typically does not participate in redox in these types of reactions, since it'll probably react with the water more so than the other halide. However, we can look at iodine, which is the weakest oxidizing agent in this series. Therefore, iodine cannot oxidize chlorine or bromine in solution, but chlorine and bromine can oxidize iodine. The second type of redox reaction that some of the halogens undergo are disproportionation reactions. Disproportionation is a fancy word for an element being oxidized and reduced within the same reaction. Only chlorine and bromine are found to undergo these types of reactions with water. And here are those reactions. They're very similar. For example, chlorine gas, when reacted with water, forms hypochloric acid, or HClO, and hydrochloric acid, HCl. Similarly, liquid bromine reacts with water to form hypobromic acid and hydrobromic acid. In both these reactions, the halogen starts out with a zero oxidation state since it's not combined with any other element. In HClO and HBRO, the halogen tends to have a positive 1 oxidation state. This means that the halogen was oxidized when forming HClO and HBRO. On the other hand, in HCl and HBr, the halogen has a -1 oxidation state, meaning that the element was reduced when forming HCl and HBr. The last group of the periodic table is one of my favorites. It's actually one of my favorites because of my research background, which I'll explain a little bit later. These are our noble gases. Now you might wonder, what's so interesting about the noble gases? They don't really react with anything. And you're right, they really don't. And this is because they have a full octet, or full valence shell. This makes most noble gases pretty inert towards chemical reactivity. However, there are some things that you can do to make noble gases a lot more interesting and a lot more reactive. In my research, we looked at exciting the electrons in noble gases to higher energy levels. This made what we call metastable atoms. Since there is a hole in the valence shell of the noble gas atom in a metastable atom, that makes those metastable atoms a lot more reactive. And I did some gas phase reactions between those metastable noble gases and other molecules. But for this course, we're going to look at something a little bit easier to understand. We can look at trends in ionization energy, and we find that ionization energy does decrease as you move from top to bottom down a group, which makes the noble gases towards the bottom of the noble gas group a little bit more reactive. Therefore, if we try to react those noble gases with extremely electronegative elements like fluorine and oxygen, we can form a small number of compounds. A good example of this is xenon, which formed probably the largest number of different molecules within the noble gas group. Xenon can combine with fluorine to form xenon tetrafluoride, where xenon has a +4 oxidation state. It also combines with oxygen to form xenon trioxide, where xenon has a +6 oxidation state. Xenon forms other compounds with fluorine and oxygen as well. where there's a range of oxidation states from +2 up to +8. Krypton also forms a handful of compounds with oxygen and fluorine. Argon only forms one compound with fluorine, while neon and helium do not. This is directly related to the differences in ionization energy. Since helium and neon have the higher ionization energies within the group, they don't form any compounds with any other elements. This includes fluorine. But since the ionization energy gets lower, then we can coax those later transition metals to react with very reactive, very electronegative atoms, such as fluorine and oxygen. Okay, so this ends our main group chemistry unit. So the next activity that you're going to do is in Top Hat. You're going to do an activity on reviewing some things to help you prepare for organic chemistry in the summer or in the fall, whenever you decide to take it, organic chemistry, if that's your choice. So this will be a Top Hat assignment, not a lecture. Originally, I wasn't going to have a lecture on Friday the 10th due to Good Friday. And I'm going to keep that tradition. Okay, there'll probably be an office hour, though, on that day due to the upcoming exam. Okay, see you guys later.